Okay, this video is going to be the Unit 9 Forces and Motion Notes 1 practice problems. We're only going to cover practice problems 1 through 6 in this video, and that is because we've already done 7 and 8 in the notes as group discussion questions. And I felt it was more important to do it then in the notes where you're kind of comprehending the material right there. But 1 and 6, I feel like you can do on your own, basically just by from the material that you learned. So number 1 says John, this guy John apparently, walks from point A to point B to C. What is the distance he travels, and then what is the displacement? Well, he walks from A to B, so like this, and then from B to C. I'm sorry I'm not drawing very straight lines, but we get the idea of what he's drawing. Okay, so the distance he travels is the total distance from A to B and then from B to C. We have the distance from A to B, that's 4 meters, but we do not have the distance from B to C. Now, many of you can tell that this is a right triangle, and that we could use Pythagorean theorem to figure out what the last part is. If you remember, Pythagorean theorem says a squared plus b squared equals c squared. Just a forewarning, we are going to use a lot of math and physics, so just be wary of that. You might need a calculator to help solve these problems with you. But anyways, we're going to solve the Pythagorean theorem. Let's say this is going to be a squared, so that's going to be 4 squared, that's 16, plus b squared, let's say this is b right here, is equal to c squared. And c always has to be the hypotenuse, so in this case that's going to be 25, because 5 squared is 25. Well, we know that b squared, therefore, is equal to 9. And then if you did this correctly, b squared can equal plus or minus 3, but you can't have a negative distance, so that rules out the minus. So in this case, it's just going to be, sorry, it's not b squared is equal to 3, it's only b is equal to 3. All right, so we were able to use Pythagorean theorem to justify our answer here that this is going to be a distance of 3 meters right here. So the total distance, going back to the actual problem, the total distance that John walked, it was 4 meters plus 3 meters. So 4 meters plus 3 meters. The total distance that he walked was 7 meters. But the total displacement was different. It's actually going to be shorter. Remember, the displacement is the shortest path from the starting point to the ending point. So in this case, going from A to C, it only had a displacement of 5 meters. All right, so that's problem number 1. Problem 2 says, look at the picture given below. An object moves from point A through B, C, D, E, and stops at point F. Find the final displacement, and then find the distance taken from point A to D. Okay, so the path, if you can't see it, I'm going to use a straight line tool to kind of make it more visible just for the sake of this video. So it goes there, then it goes up, then it goes over again, and it goes sideways like that, and then it goes straight up after that. So we want to figure out what those distances are, and then find what, actually the first question is, what is the displacement? So he started at point A right here, and then he ended at point F, okay? Did he move anywhere in the X direction? No, he did not. In the entire X direction, he's staying, if this is the X axis, he's staying on this 2 line the entire time. In the Y direction, he did move how many squares? He's going from 2 to 4, 4 to 6, 6 to 8, 8 to 10. You could count that if you wanted to, but we're going to do the difference in Y is going to equal 10 minus 2. So his displacement was 8 meters. Okay, so that's his displacement. That's the easy part. The hard part is finding out what's the distance going from A to D. It's not asking for the total distance. It's just going from A to D. So first we need to count for A to B, then B to C, then C to D. Okay, so we got to figure out what all of those are. Well, fortunately for us, they're straight lines that are going to either go horizontally or vertically. So horizontally, it's going from 2 to 10. So 10 minus 2 gives us a difference of 8 meters. So that's going on the x-axis based off of that. From B to C, that's based off of the y-axis. So we're going from 10 to 2 again. So 10 minus 2. The difference there is 8 meters. And then going from C to D, the difference there is 10 to 6. So 10 minus 6 gives us 4 meters. You add all of that up, so the distance traveled is going to equal 8 plus 8 is 16 plus 4, that's 20 meters. So there's your displacement, and there's your distance. That's problem number 2. Problem number 3 says, consider a football coach pacing back and forth along the sidelines. The diagram below shows several coaches' positions at various times. The coach moves from position A to B to C to D. What is the coach's resulting displacement and distance of travel? So again, we're looking for 2 separate things. We're looking for displacement, which we'll put over here, and then we'll do distance, which we'll put over here. Okay, so if he's going from A to B, then from B to C, and then C to D, so he's kind of pacing back and forth. He's going this way, and then this way, and then this way. All right, so that's kind of like the path traveled. So the total displacement is from start to end. So if he's going from, let's say, 50, that's the initial point, and then we're going to have to subtract, and then he goes all the way, this is 0, so this has to be minus 5, because if this is minus 10, it's got to be in between. So 50 minus negative 5, well, when you minus a negative, you actually add them, so 50 minus negative 5 is 55 meters. The displacement's the easy part. So that's displacement. The distance, we got to do it the same way as before. A to B, then B to C, then C to D. Okay, so going from A to B, that was the difference. He started at 50, and then he went all the way to 15. So that's a difference of 35, and this is yards. So let me actually correct this unit here because I got that wrong. I'm so used to using meters that I wasn't paying attention to the unit. He's walking in yards, not meters. So this is yards. Then you went from B to C. So we can say that he went from, we can do 35 minus 15. Again, I know this is 35 because it's right in between 30 and 40, and this is 15 because it's right in between 10 and 20. So 35 minus 15 gives us 20 yards. And then he went from C all the way to D. So he went from 35 minus negative 5. And again, like before, when we subtracted a negative, we have to add it. So that's 40 yards. All right. Then you add all of that up. 35 plus 20 gave us 55. And then 55 plus 40 gave us a distance of 95 yards. Okay, so there is problem number 3. All right, problem number 4 says, what will be the resultant velocity of the plane if the wind had the same direction as the plane? Do a sketch similar to the one of the picture above. We did this one in the notes, but we're just going to do it again to cover what does resultant velocity mean, right? So I'm just going to underline those words, resultant velocity. I'm not going to sketch a plane. I'm actually just going to paste an image of one. So there's our plane, and according to the notes, if I remember correctly, it was traveling at 100 kilometers per hour, and then there was a wind. So the wind was actually blowing with it at 25 kilometers per hour. But the wind is not only blowing in front of it, it's also pushing it from behind, right? So it's 25 kilometers per hour. So in this case, the plane is feeling like an assist from the wind. It's kind of like if you were to go out for a run. Running into the wind is much more difficult than running with the wind against your back. So in this case, the wind is actually pushing the plane, and the resultant velocity of this, you would add these together. So the resultant velocity is 125 kilometers per hour. But like I mentioned before, we did this in the notes, so this problem should just be a review. Number 5 says find the velocity in meters per second of a swimmer who swims 110 meters towards the shore in 72 seconds. So we've got some numbers here, and whenever we have numbers, we got to write down that data. So we have 110 meters, and then we have 72 seconds. And let's clarify what those are. So 110 meters. Meters is a unit of distance, and then seconds is a unit of time. All right, and the question asks find the velocity in meters per second. So that's underlined for us. So we have meters and we have seconds. So we're good. So what is velocity? That's the question. Well, do we have a formula that associates all three of these? Yes, and we've actually learned it from Unit 7. The speed is equal to distance divided by time. All right, so, or the velocity here in this case. So velocity is going to equal to 110, so I'm just plugging in the numbers here, meters divided by 72 seconds. So meters per second is a unit. All right, so if I put that into my calculator, I get a velocity of 1.5, and I'm going to round 3 meters per second. Now, that's the numeric value of this problem. But remember, velocity is not the same thing like speed. This is just a speed. Velocity not only has a magnitude like speed, but it also has a direction. So you have to tell me in what direction. Well, in the problem, it says a swimmer who swims 110 meters towards the shore. So what you could say is that he has a velocity of 1.53 meters towards the shore. So that's the only direction that we have. We don't know if it's east, west, up, or down, but it does give us a direction. So it's 1.53 meters per second towards the shore. Last problem, number 6, says find the velocity in meters per second of a baseball thrown 38 meters from the third base to first base in 1.7 seconds. Okay, so we got some numbers. So again, write down all your numbers. We have 38 meters. And then we have 1.7 seconds. So again, we know that this is a distance and we know that this is a time. And the question is asking for a velocity in meters per second yet again. So we have v is equal to something. And we should know the equation that v, the velocity, is equal to the distance divided by the time. So let's go ahead and plug in those numbers. We have 38 meters divided by 1.7 seconds. When I put that into a calculator, let me go ahead and do that. 1 second. 38 divided by 1.7. I get a velocity of 22.35 meters per second. But yet again, I am not done with this problem. That's a velocity that gives us only a magnitude. I also need the direction. So I could say, if you're reading the problem, the only scenario that we're given is that it was thrown from third base to first base. So what you could say is toward first base. All right, you could also technically say away from third base, but that's not technically accurate because you have to tell it like where it's going. From third base could mean that it could be going to home plate, could be going to second base, could be going to the outfield even for some bizarre reason. But you would have to describe like where it's going, not where it's coming from. So toward first base would be the correct answer to put there. So that concludes the practice problems 1 through 6. Be sure to review the notes in order to get the answers to practice problems 7 and 8.